Hello and welcome. In this video, I'm going to take a look at another application of the derivative, which is called linear approximation. Now, linear approximation you can understand because we've been looking for slopes of tangent lines, and so tangent line being a linear function, it's all kind of related here. And the topic of linear approximation will also allow us to talk a little bit about differentials, and that's going to be something that also is very useful to know about before going into integral calculus. So let's take a look here. What are we talking about when we're looking at linear approximation? Well, if you take a function y equals f of x, we can find the equation of the tangent line using point slope form. Y minus y naught equals m times x minus x naught. Now, if we're given that we want that the tangent line at x equals a, then that means that our x naught is simply just a. It means y naught is the value of the function evaluated at a, and the slope is the value of the derivative evaluated at a. And by rearranging that, we can make that look like a function. So that the equation of the tangent line is really just the function L of x equals f prime of a times x minus a plus f of a. And we call this the linearization of f at x equals a. Now, what can we do with that other than just talk about the slope of that line? Well, when we take a look at plotting the function here as well as the tangent line, you can see that for a certain region around a, as long as we're choosing values of x fairly close to a on either side, if we zoom in, we can see that it really doesn't matter whether we pick a point on the blue or red curves here, they're pretty much exactly the same. After a certain point in time, the blue tangent line doesn't do a very good job of approximating the red curve, but certainly as long as we're sort of within some sort of small range of values on either side of A, the blue line and the red curve are nearly the same. So this is a great use for the approximately equal to symbol. We can say that f of x, those are the values for y on the red curve, is approximately equal to the values of L of x, the linearization of f at x equals a, as long as we pick values of x close to a. Now that's the idea about linear approximation. Knowing that the linearization is a linear function, it's very easy to plug numbers in and compute y coordinates. And that'll give us a very quick way of approximating values on the function f of x, which may be a much more difficult function. We can actually use this to even be able to compute square roots of numbers by hand, which we might not otherwise be able to do without a calculator. Here's an example. All right, let's suppose we have the function f of x equals the square root of 10 minus x. Well, let's look at the linearization of this function around x equals 1. So to do that, we know, of course, x equals 1, but we need to know what f of x is. F of 1, if we plug that in, it's just going to be the square root of 10 minus 1, which is going to be the square root of 9, or just 3. So this is really just, finding this equation of the tangent line at the point 1, comma 3. Now we also need to know the slope, and the slope is given by f prime. So let's calculate the derivative in terms of x first, and we'll have to use the chain rule. You could rewrite this function as 10 minus x to the power of 1/2, and then the derivative is going to be 1/2 times 10 minus x to the power of negative 1/2. Now don't forget, there's one important thing here missing, and that is using the chain rule. Since we have 10 minus x as the inside function, we need to multiply by the derivative of 10 minus x, which is negative 1. And that means that our derivative can be written in the form negative 1 over 2 times the square root of 10 minus x. Now that doesn't get us the slope just yet until we plug in x equals 1. And luckily, plugging 1 in, we get a very nice perfect square here. 10 minus 1 is 9, and the square root is going to be 3. So negative 1 over 2 times 3 is negative 1/6. And these are the two important pieces of information that we need in order to give the equation of a tangent line. We need a point, and we need slope. Of course, these pieces of information can simply be plugged into this equation L of x equals f prime of a times x minus a plus f of a, as long as you remember that equation. Otherwise, if you just know point-slope form, you can come up with it for yourself. The linearization, L of x, is equal to f prime of a times x minus a plus f of a. And we can easily expand and simplify. And the linearization can be written out as -1/6 x plus 19 over 6. And this worked out great because, of course, this function has a very nice value when we plug in x equals 1. It's just the square root of 9. Now take a look at part B here. We want to estimate the square root of 9.5, which of course is very close to the square root of 9, so it's going to be very close to 3. But of course, it's pretty hard to calculate the square root of 9.5 without having to use a calculator. But we can try to estimate that value using this linearization. When plugging in x equals 1, we get the square root of 9. If we plug in x equals 0.5, we'd end up with a square root of 9.5. But plugging in 0.5 into f is going to be very, very close to finding the value of L of x evaluated at 0.5. So for part B, we can recognize that the square root of 9.5 is precisely the value of the function f evaluated at 0.5. That is going to be very, very close. We'll use the approximation symbol, approximately equal to the linearization of f at 0.5. Because we found the linearization at x equals 1, and 0.5 is going to be kind of close to that little local neighborhood of values are close to a. As long as we don't go too far from x equals 1, our linearization and the red function should be fairly close to the same. So we can just plug 0.5 into our linearization and say, well, that should be pretty close to the square root of 9.5. So square root of 9.5 is approximately equal to the linearization -1/6 times x, which is 0.5, plus 19 over 6. Now, it might make more sense to just use fractions here. 9.5 is approximately equal to -1/6 times a half is -1/12, plus 19 over 6. And 19 over 6 would be 38 over 12. So adding these together, square root of 9.5 is actually approximately equal to the fraction 37 over 12. Now, depending on how well you know fractions, you might be able to convert twelfths to decimals without using a calculator. Of course, you could also use long division here. 37 over 12, if you wanted that as a decimal, is going to be equal to 3.08 and 3 repeating. Now, if you want to see how close we actually are, the square root of 9.5 unfortunately can't be represented as a fraction. But now that you can see this fraction 37 over 12 is equal to 3.083 repeating, we could check and see how close that is. If we type this into a calculator, the square root of 9.5 as a decimal is 3.082207001. And so you can see just how close our estimation of 37 over 12 is to the actual value. We have a very nice fraction that's very, very close to the actual value of the square root of 9.5. And that's where the use of linear approximation comes in handy. Now, this leads us to another topic as well for estimation, and that is using differentials. And it's kind of a similar process. All right, where we get differentials from is maybe best thought of as using Leibniz notation here. Leibniz notation is when we write dy by dx, and it's kind of handy to see that sort of look like a fraction. It's a change in y over change in x. And if we know the rate of change dy by dx at some point, well, these dy and dx's are known as differentials, like very, very small changes in y and x. When we're using the limit definition of the derivative, we're trying to find the slope between 2 points that are getting infinitely close, which gives us infinitesimally small rise and run. So that's where you can think of a differential. Now, suppose that we change x by a small amount, and then the corresponding change in y would then be delta y. So here I've got some sort of relationship being this red curve here. It's a relationship between x and y. It might be the form of an equation. It might be a function. And if we take up some sort of known quantity x and y, and we change x slightly, we will see what the new value is for y, and that would be y plus delta y. Now, delta x and delta y can be positive or negative changes. It doesn't really necessarily have to look like my picture here. Well, suppose we wish to maybe take some change in x and estimate how much y is going to change by. The nice thing here is that the slope of the secant that connects the exact 2 points here, the slope of that line is delta y over delta x. And it's going to be very, very close to the slope of the tangent line at xy, which has a slope of dy by dx. Those are approximately equal to each other. So if we wish to estimate the change in y, that is approximately equal to the derivative evaluated at the initial point xy multiplied by our change in x, so long as the change in x is quite small. So this is how we can approximate the change in y and not have to compute it by actually evaluating 2 different points and subtracting to get delta y. We just need to calculate the derivative, which could be very straightforward, find out what that derivative is at the point, and multiply by how much we want to change x by. Well, let's take a look and see where this might be useful. All right, let's start off with a cylindrical rod of aluminum, or aluminium, depending on what part of the world you're from. Let's say it has a length of 20 centimeters and a radius of 5 centimeters. Now, if we shave off 0.05 centimeters or 0.5 millimeters thickness off of the rounded surface, let's see how much material is actually removed. What volume of material is removed? So we've got a cylindrical rod with a length of 20 centimeters, or we could express that typically as height when we're talking about a cylinder, and it has a radius of 5 centimeters. Now, it's going to be helpful to know the volume. At any time that we have the volume of some kind of cylinder, whether it's a circular cylinder like this or triangular cylinder or any kind, you just need the area of the base times the height. And being a circular base here, pi r squared multiplied by height. Now, we're going to shave off a little bit of material. So we are going to essentially be trimming off a very small amount of material from the outer sides here. And that's going to be a very, very minute change in radius. Compared to the 5 centimeters, shaving off 0.05 centimeters is not going to be a very big difference. That's really going to be our delta r. Our delta r is going to be subtracting 0.05 centimeters from the overall radius. And we want to know approximately what volume of material is removed. So we want to find out what delta v is. Now, of course, you could plug in a radius of 5 centimeters and a height of 20 centimeters, and then repeat that calculation with a radius of 4.95 centimeters and a height of 20 centimeters, and then subtract to get the exact difference. But we just want to do a quick estimation. So to find delta v, we could say that that is approximately equal to the rate of change of volume with respect to radius multiplied by the small change in radius. So we just need to find the derivative dv by dr. And since height is not going to be changing and we're not shaving off anything off the length, h is just going to be a constant. So the derivative dv by dr, we have pi and h as constants, and the derivative of r squared is just 2r. And so we end up with 2 pi rh. And by no coincidence, that is actually also the surface area around that outer rounded surface. Now, if we just use this with our equation for delta v, we can say that delta v is approximately equal to 2 pi rh times delta r. Now we can plug in all of our numbers. Delta v is approximately equal to 2 times pi times our radius of 5 centimeters times our height of 20 centimeters times the change in radius, which is negative 0.05. And if you take a look at the units, we've got radius in centimeters, height in centimeters, and a change in radius in centimeters. So we end up with centimeters cubed. We'll end up with a negative value because the volume of the cylinder is decreasing. So the approximate volume that is lost off the material is 10 pi cubic centimeters. Now, it's using this idea that allows us to take the idea of what this Leibniz notation really means and sort of extend it. This equation dv by dr equals 2 pi rh. What we can really do with that is we can just treat that dv by dr as though it's a fraction. We just say that the differential in v is equal to 2 pi r h dr. dr is the differential of r, and dv is the differential of v. And so using this idea, we can just say that change in volume is approximately equal to the differential of volume. And that is equal to 2 pi rh times the differential in r. In general, whenever we are given a function y equals a function f of x, then we can write Leibniz notation dy by dx equal to f prime of x. And the differential of y is simply equal to the derivative evaluated at x times the differential in x. And it's this nice little notation there that if we know a small change x, we just plug that in for dx, we multiply by the derivative, and we end up with an estimation of how much y has changed by. So, dx is what we plug in, and dy is an estimate of the change. So I hope that gives you at least a little bit of an idea about why tangent lines are kind of important. It's not like we're just going around finding tangent lines of random things. It's just when we look at a natural phenomena, we kind of want to know, if I change this by a little bit, how much is that going to change by? We can estimate that by just turning some sort of interesting behavior into a nice, easy, linear behavior. It makes it easy to plug a number in and estimate what's going to happen. That's the idea of just using slope to estimate change. Well, thanks for watching. I'll see you in the next video.